Okay. Well, now we've finished the topic of control of stability of nonlinear systems. Today we are going to start with the control of nonlinear systems. So in the control we have a couple of methods. Currently we have feedback linearization, which we can maybe start today if time permits. And we have also sliding mode control, and we are going to try to cover it if the time permits towards the end of the semester. So here let us say control of nonlinear systems. In general, we divide the control problems into two categories. This is an old categorization of control problems. So when we look at general control problems, we can divide them into two. The first type is regulator problems. Regulator, or sometimes these are called stabilization problems. And the second type, they're called servo or tracking problems. Okay. So these two types of problems change in the way that they counteract different signals in the systems. In regulator problems, we manipulate the system input to counteract the effect of disturbances or initial conditions, and/or initial conditions. Okay. So these are regulator problems. Remember, control is choosing the input of a system to make the system do something that we like. Okay? So what control does in the overall is that it chooses the input to the system to make the output of the system do something we like. So in regulator problems, we choose the system input to counteract the effect of disturbances or initial conditions. There might be, of course, there are some common examples here. For example, temperature control of a room. Or the second example is altitude control. Altitude or attitude. It might be, both of them might be regulator problems. Altitude control of an aircraft. Okay. So we want the temperature of this room to be at a constant value, and there are disturbances, air coming from the windows, or the outside temperature is a disturbance here, and we would like to control the temperature at a constant value, keep the temperature at a constant value against the disturbances. Or altitude control, we generally would like to fix it at a constant altitude, and then there are many disturbances which can counteract our control effort. So in servo problems, we manipulate the system input, the same thing, control, to keep the system output close to a given reference input trajectory. So in this case, the reference input is actually changing. In regulator problems, usually the reference input is a constant. So for example, we usually try to keep the temperature of a room at a constant value, or the altitude we try to keep it at a constant value. And in servo problems, the things change a little bit. In this case, disturbances are less important, and the reference input changes are more important, actually. Okay, so the reference might change in a fast way, and what we want is that we would like the output to follow the reference input as closely as possible. So the emphasis is on the reference input. So we are trying to keep the output close to the reference input. And for example, there might be some examples here, and these examples are, for example, making a robot arm follow a trajectory, or making an aircraft fly along a specified path. So if I draw the general, and in this case, the systems which would achieve such tasks are called sometimes servo mechanisms. Okay, that is the name given to the systems. For example, you might have heard the name servo motor. It is this type of system. When we have a control loop, we have a controller here that is called a feedback controller. And here is the system that we would like to control, that is called the plant. And that is feedback loop. So we have the reference input and we have the disturbance here, W of t. The task of the controller is to choose the input that is coming to the system. Okay? So this W of t is the disturbance entering into the system, and this R of t is the reference. And these two problems differ in what they're trying to counteract in this system. So here in the regulator problems, what is less important is the reference signal. Because reference signal is usually a constant in regulator problems. And what is more important is the disturbance signal and the initial conditions of the system. In servo problems, things reverse their places. Okay? In servo problems, disturbance is going to be less important, and the fast changes in the reference would be more important. Okay? In that case, the control is mainly to follow the fast changing reference input. Okay, so the signals would change their places. And actually, I can actually say that sometimes the distinction between these two systems are not really that clear cut. Okay, so sometimes this distinction is actually is blurred to some extent, because what is going to happen when the reference is changing and the disturbance is also a non-negligible signal. In that case, we have a servo problem where the disturbances would be important, so the controller should act in both the regulator and the servo manner in that case. So sometimes the distinction between these two systems, sometimes there might be control systems which cannot be called clearly a servo mechanism, or they might not be called regulators from the start. Sometimes the distinction is not that clear. But these are historically the control problems that people how the people would classify the control problems. So as a second thing here, so this is a general introduction for the control of nonlinear systems, nonlinear or linear systems. It really does not matter. So we're going to now try to look at controller types. So in this case, we will consider two different types of controllers. One is the feedback controller, which we already saw in many courses in this department. So feedback versus feed-forward control. Let us try. In general, I will actually draw a block diagram that is including both of these controllers. So I have a feedback controller here. This is the classical feedback controller structure. That is my reference input, and that is the error signal E of t, and the controller is choosing the input. We have another type of controller that is called feed-forward controller, and in that case there is a disturbance signal actually coming here. And feed-forward controller has the following structure. In general, a feed-forward controller can get its inputs from either disturbance or from the reference signal, and it would provide its output to the input of the system. Okay? That is what a feed-forward controller appears in the topology of control systems. So in general, this feed-forward controller is taking its inputs from the reference signal, or it's taking its inputs from the disturbance signal, and it is actually providing an additional input to the feedback controller in this diagram. So what type of thing that a feed-forward controller do? In general, it is used, let us write, a feed-forward controller is used to cancel known disturbances in regulator problems. So if you have a way to measure the disturbances somehow, and in such a case, a feed-forward controller might make the task of a feedback controller easier by measuring the disturbances and by using a feed-forward controller, the task of the feedback controller might become easier. This is the first task of a feed-forward controller. The second one is to compensate for the fast changes of the reference input. In tracking problems or servo problems. Okay. So in both of the type of these control problems, feed-forward controller can be useful. And the first thing that it can be useful for is to cancel known disturbances. So if it can take measurements from the disturbance, then it can help cancel the disturbances in the control system. In a regulator problem or in a servo problem, it can get measurements from the reference input, and then it can try to compensate the effects of the fast-changing reference input in the feedback loop. Okay, that is a second task. And in the overall, it is used to reduce the load of the feedback controller. In general, the input that we are selecting is the summation of the feedback controller input and feed-forward controller input. Okay? So in some way, when this feed-forward controller takes some action, then it's going to reduce the load of the feedback controller. So here let us try to look at an example. In this example, I will consider the temperature control of the room. In this case, we have the system that we would like to control. It is the room itself, and we have our actuator. So this is an air conditioner. And we have a feedback controller here. Which gives input to the air conditioner. We have our feedback loop, and this feedback controller takes the error signal, and we have the reference R of t. And then we're going to add this disturbance signal is affecting the room. Okay? It might be the outside temperature, for example. Okay? The outside temperature is acting like a disturbance on the system. And then we're going to add a feed-forward controller into this structure. Okay? So here, what is necessary for the feedback controller to actually work? So in general, when this feedback loop is working, what has to happen for the feedback controller to work is that there should appear some error signal in the system. Suppose that this reference is actually constant. Let us say that it is 27 degrees. Okay? So for the feedback controller to work, whether to make the room warmer or cooler, there has to appear some error signal in this part. Okay? So here, the room temperature should actually change before a feedback controller can actually take action. Okay? For example, if this is 25 degrees, then we're going to start to heat the room. Or if it is larger than 27 degrees, then we are going to start cooling the room. But what is important here is that for the feedback controller to be able to work, we need an error should appear first. Okay? Without the error signal, without the appearance of the error signal, feedback controller is not working here. Okay? So the system temperature should deviate maybe significantly from the reference signal before a feedback controller can actually take action. Okay? So how can we avoid this? How can we make that error signal smaller actually before a feedback controller start working? Suppose that you know the temperature forecast for tomorrow. Okay, suppose that your room is currently at 27 degrees. Okay, and suppose that you know that tomorrow it's going to be a very, very cold day. Okay, much colder than today. Okay, in that case, if you keep the feedback controller, then what has to happen in the system in the room is that tomorrow the room is going to cool down. And then there will appear an error signal here, and then feedback controller is going to start working, and then it's going to try to pull the temperature back to its desired value. Okay, but the first thing that has to happen is that tomorrow the room is going to cool down first, and then the feedback controller is going to start working, and it is going to pull the temperature back to its reference value. Okay? If we really do not want to do this, we can actually use a feed-forward controller there. Okay? So, for example, what we can do is that we can try to measure this disturbance signal. So we will know what is going to be the temperature outside before there appears an error in this system. Okay? So we will measure this, we will put a temperature sensor outside maybe, and then we will measure this disturbance. Okay? So by measuring this disturbance, actually, a feed-forward controller can actually start heating the room before actually it cools down. Okay? So by measuring the disturbance, we can start heating the room before actually the room cools down and before an error actually appears in the system. That is going to be the task of a feed-forward controller. Okay? It's going to measure the disturbance, and it is going to try to compensate for the discrepancy before an error for the feedback controller to work actually appears. Okay, so this is just an example application. So you can put some additional sensors outside the room, and then you can based on the results of the measurements of those sensors, you can start your control action before an error actually starts to grow in the system. Okay. So we are going to be using this type of feedback controller idea in the control part of this course. And what we are going to do is that we will start designing controllers by a method that is called feedback linearization. And we are going to design tracking controllers. So we will actually design servo controllers. What this means is that we will want the output of the system to actually, output of the nonlinear system to follow a reference signal trajectory. Okay? And while doing that, we are going to use a feed-forward controller, which is actually going to take its measurements from the reference signal. So if the reference signal is changing quite fast, this feed-forward controller will actually start taking action before feedback controller starts to work. So this idea is going to be useful for us in designing our controllers using so-called feedback linearization. So let us say feedback linearization. So before starting with the theory here, what I'm going to do is that I will be working on a simple example, an example that we are familiar with so far in this course. So here, in this example, we will try to design a feedback linearization-based controller for the pendulum system. Let us say tracking control of a pendulum using standard linearization. So the first thing that I would do, I would design the controller using standard linearization. This is going to be a tracking controller, as I told you. So in that case, you will actually understand how such a controller can be designed. And then we will see the drawbacks of standard linearization in our design. And then we will go into the topic of feedback linearization. So for this example, the system is given as follows. We have the pendulum system here. So I have the angle theta. The friction is V. And let us say that we are actually applying a torque input to the pendulum, which is shown as U is equal to tau. Okay? We have the gravitational effect as mg, and let us say that we have x is equal to theta and theta dot, which is our state vector, and the state equations are x1 dot is equal to x2, and x2 dot is equal to u minus sine x1 minus 0.2 x2 here. Okay? And we define the output of the pendulum as the first state variable, which is the angle. Okay? I'm assuming that the initial conditions of the pendulum, x10 and x20, are both equal to 0. Okay? And here the aim is the following. We want the pendulum angle to follow a reference input R of t as closely as possible. Okay. So that is our aim. So the question is, how should we choose the torque input U of t to the pendulum in terms of R of t, x1 of t, x2, and y. Okay? How do we choose this control input? That is the aim of the controller. Okay? It's going to choose the input to the system to make the pendulum do something that we like. Okay? So here, what I want to do, for example, is that if R of t is a times cosine t, okay? Let us say that R of t is this sinusoidal signal. Okay? In that case, what we want is the following. So this is time, and cosine of t is a signal that is looking like this. And the pendulum output is going to be initially at the origin. Okay? So here, this signal here is R of t, okay, with respect to time. It is a times cosine of t, so this magnitude is actually a. And the pendulum system is going to start at the origin. Its angle is going to be the downward equilibrium point angle, because x1 of 0 is equal to 0. Pendulum angle is going to start here, and we will want the pendulum angle to follow this trajectory. Okay? So we would want the pendulum angle to actually converge on this reference trajectory and to continue following it continuously. Okay? That is actually our aim. So for that purpose, what we are going to do is that I'm going to be defining an error signal, the discrepancy between the reference and the actual output of the pendulum. So this red signal here is nothing but the output of the pendulum. Okay? And what we are going to do is that we will want to define what the error signal here is. So when we define the error signal, it is going to be the reference signal minus the output signal. Okay? It is going to be R of t minus y of t. And then we could actually specify the following control A. We want E of t going to 0 as time t goes to infinity. Okay? That is what we would like to do. So the first thing that we're going to do is that we will try to design this tracking controller using standard linearization. Okay? And we are going to first apply standard linearization to the system, and then we will design our tracking controller. So here, the first thing to do is that I would like to linearize this system around the downward equilibrium point. So I will choose the equilibrium point, which is 0, 0, and I will choose the equilibrium input to be 0. Okay? In this case, the equilibrium input is 0 torque, and then the downward equilibrium point is an equilibrium point. And around that equilibrium point, I will apply linearization. So you can actually use the earlier theory here. I will just write the linearized system equations. I will not repeat the linearization procedure here. I think you all know how to linearize such a system and around that equilibrium point. And if you try to do that, you will see that it's just going to replace the sine x1 with x1 itself. Okay, that is the approximation that the linearization is going to do. X1 dot is equal to x2, and x2 dot is equal to u minus, instead of sine x1, I will just write x1 here. That is what I'm going to get at the end of the linearization. It is going to be 0.2 x2. This is going to be the linearized system dynamics using standard linearization. Remember here we define z is equal to x minus xe, and then we find z dot is equal to f times z plus g times u and g times v here. We define v is equal to u minus ue here, and then we find f and g matrices, and here f is the Jacobian del f over del x, evaluated at x is equal to xe, u is equal to ue, and here g is del f over del u, evaluated at x is equal to xe, u is equal to ue. And if you do these calculations, you're going to see that this is going to be the linearized system approximation for us. Okay? That is, here in this case, z is going to be x, and v is going to be equal to u. Okay? Because both of them are equal to 0, and this is going to be the system that you're going to obtain after the linearization. And based on this linearized approximation, we're going to try to design our feedback linearization, our controller, which is the tracking controller, which would make the output follow a reference trajectory as closely as possible. So here, what is the bad thing about this linearization? In this linearization, what we did is that we replaced sine x1 with x1. So if this is x1, and then if this is sine x1, what we did was the following: we replaced sine x1 with x1 itself. Okay? So this is our approximation in this case. Okay? We know that such an approximation is quite valid if x1 takes values which are close to 0. Okay? But we know that the approximation is start becoming invalid when x1 would get far away from the equilibrium position. Okay? So for large x1 values, this approximation is no longer going to be valid. So here, and in this example, we want the output y. Y is equal to x1 here. We want the output y to follow this reference trajectory as closely as possible here. So if this a is small, this approximation is still going to be valid because here this y, which is the x1 signal, if a is small, x1 signal is not going to deviate from 0 much. Okay? But if a is large, in the case that we want the pendulum angle to follow angle values in a large operating range, in that case, that approximation might not be valid. Okay? And in such a case, we will see a deterioration in the performance of our controller when we design it. Okay? So we're going to try to illustrate these drawbacks on a MATLAB simulation actually when the time comes. But here the thing that we're going to do is that we will first design our controller. For designing our controller, I'm going to start from the output signal. We know that the output signal is equal to y is equal to x1. And our aim here is going to be to make the error signal go to 0. We will start from y is equal to x1, okay? And then I will start taking derivatives of y until the input appears on the right hand side. So let us take the derivative of y. This is going to be y dot, and it is going to be actually x1 dot, okay? And this x1 dot is equal to, by the system equations, x1 dot is equal to x2, okay? So we get the equation y dot is equal to x2. The input did not appear on the right-hand side of the system. This is going to be a design procedure at the end, okay? But here, the first step of the design procedure is going to tell us that take the derivatives of the output until input appears on the right-hand side, okay? So currently, the input did not appear yet, okay? So I will continue taking the derivatives. So I will calculate y double dot. Y double dot is going to be the following. It is going to be x2 dot, okay? And x2 dot is given there. It is u minus, I have x1 minus 0.2 x2 here, okay? Now the input has actually appeared on the right hand side, okay? So that is why I'm going to stop here. Our design procedure is going to tell us that we need to take the derivatives of the output until input appears. And the smallest order of derivative where the input appears on the right hand side is going to be called the relative degree of the system. So in this case, the input appeared on the right hand side when we take the second order derivative. So that is why we are going to call the relative degree of the system as 2. Okay, that is the minimum order of derivatives before the input signal appears on the right hand side. And here, that derivative order is actually 2. In the second order derivative, the input appeared on the right hand side. So now, before I continue, I will make some cleaning on this equation. So this is y double dot is equal to u minus x1 is y. Okay. I know that x1 is y, minus x2 is y dot, okay? So I will just write y dot here. And I will collect all of the y-related terms on the left-hand side. All linear y-related terms would be collected on the left-hand side. So we will write y double dot plus 0.2 y dot plus y is equal to u, okay? Well, this is going to be the equation that we obtain, and actually this is nothing but the differential equation representation of the pendulum, linearized pendulum system. Okay, that is what we have. And then what we're going to do is that we will start choosing this u. Okay, that is going to be the controller equation. Okay, so I will choose u here in the following way. The input u is going to be formed out of two components. The first component is going to be the feed-forward part, and the second component is going to be the feedback error part. Okay? So here, the first part is going to be related to the feed-forward controller. Okay? And this is going to be r double dot plus 0.2 r dot plus r, okay? So we are going to replicate the left-hand side of this equation in terms of the signal r, okay? That is what we are going to do, and this part is going to form the feed-forward part of the input. Okay? And the second part is going to be related to the feedback controller part, okay? So I will write the second part as k0 times E plus k1 times E dot here. Okay? This part is going to be called the feedback part. Okay? And this feedback part is actually going to be formed out of the error signal here. Okay? And here I will continue including the derivatives of the error signal until the order one less than the derivative of the orders on the left-hand side here. So if this equation contained a y triple dot, for example, in that case I would have added one more term here as k2 times E double dot. Okay? So that is how we're going to form our controller, and then this controller is going to include both a feed-forward controller and feedback controller. And we're going to see the effects of these parts when we go further on this topic. Bugün anket varmış. Siz onun için geldiniz herhalde. O yüzden bir 10 dakika erken çıkmam gerekiyor. Yani beni buradan kovuyorlar. Dolayısıyla size feedback linearization'ın detaylarını anlatmak çok isterdim ama heyecanla çarşambayı beklemek durumundasınız.